So thank you very much for joining this talk. I'm very happy to be here. I want to start by saying my thank yous first, just so I don't forget. First of all, I want to thank my lovely wife Mihaela, who joined me on this trip. It's our first time here in Scotland. It's been a wonderful experience so far. So it's great to have you here. I also want to thank the organizers, Ross, Pete, Ray, and the whole team that's organizing this event. And I want to thank the British Bulgarian Business Association, DESI, is here in the room, and the Bulgarian commercial attaché to the United Kingdom, Krasi, who's also in the room. We're here as part of a delegation, a trade mission that is trying to promote bilateral trade between our countries. So I'm very happy with the trip so far. Perfect. It's full of Bulgarians in the room now. Yeah, this is perfect. I want to show you examples today of how we can make big data work for us. And I'm choosing my words very carefully because we've obviously reached the point where we can harness technology to collect, process, model, and produce outcomes. And what I want you to take away from this discussion is a very positive feeling that we can actually solve some of the most complex problems related to public transport in particular in cities. And I've divided the presentation in two parts. In the first part, I'm going to talk about context around future mobility, so prospects and challenges, and context around public transport in particular. And afterwards, I'm going to provide the examples, talk a little bit about the technology, and talk about the value of the outcomes. And the reason why I want to talk about context first is because cities are extremely complex, broken systems with many agents interacting on many different levels. And there's a lot of wonderful software that is being developed and sold in batches, but it's rarely addresses in necessary depth the contextual problems that cities have. We have to be aware about context for two reasons, at least. First of all, I want to make a point that to resolve complex problems in cities that affect numerous agents, peoples, enterprises, businesses, it's better to use a bottom-up approach instead of trying to fit software to the problem. It's better to understand the context, to define the problem, and then use the plethora of open source technology and different software components to build the technology for the specific problem. And there's an issue with this approach, and the issue is that it's not very commercial, in the sense of it's difficult for companies to invest in such software products and reproduce them and build sales pipelines and make profit of them. So if you and here's the second point about context. If you monitor the pulse of the discussions in social space on sustainable growth, climate action, resilience planning, urbanization, and all of these megatrends, you will identify at least three archetypical types of voices. There are the skeptics, there are the advocates, and there are the critics. And the skeptics are basically people who, for the most part, worked as civil servants for, let's say, 30 or so years. They were advocates for a long time until their energy levels got totally depleted. And they weren't quite able to see positive change being driven all the way through the system, producing better outcomes than the one we're seeing today, and for which we're paying the price. The advocates are obviously people trying to, well, their rhetoric is very specific, and I think I fall in this group as well. We speak about generosity. We speak about investing in city solutions as investment, not as charity. We have a hard time talking to the critics, and the critics are normally people who know how to make money very well. People who know how to make money, when they take their masks down, they will tell you that working in business to government, on business to government deal flows is sticky business. And they will often use terms like profitability, year on end, growth, investment, unicorns. And why I'm bringing this up, we don't need to mitigate this situation immediately. What we need to do is we need to be aware about this rift in social dialogue. And if we understand the mental models and the archetypical relationships between these types of people and their behavioral beliefs, then we can navigate and we can see a bigger rate of adoption of the solutions that we have ready, because there's no point in holding an uncut diamond in your hand if you cannot cut it and sell it and display it. So that's why I'll be talking about context. So that was a long introduction, but a necessary one, I believe. And generally, I want to celebrate the fact that we've learned how to swim by learning how to make data work for us and not necessarily focus on the depths of the ocean and what lies beneath. So 10 minutes gone. And I will try to run through the other slides in another 10 minutes so that we can have a discussion afterwards. So won't discuss the title now. We can do that afterwards if you like. I hope you've seen the movie. It's WALL-E. And why I'm doing what I'm doing, because I hope my kids won't end up in a chair sucking milkshakes when they're not in cryogenic sleep, flying millions of light years looking for a new planet to colonize because we sort of destroyed our planet. So mobility has 4 dimensions, obviously: land, air, sea, and space. And I'd hate to think that we'd reduce it to just one. The United Nations estimates that global population will grow by 2 billion in the next 20 years. And if about 50% of global population lives in cities today, they estimate that 75% will be living in cities within 20 years. So urbanization is a serious threat to our cities and densely populated areas. You're seeing what's going on in the world now with the war in Ukraine. Obviously, energy crises like the one we're seeing now are probably going to reproduce themselves again, or we should be prepared for such scenarios. Climate action. If you've ever wondered why the temperature in cities rises, it's because concrete absorbs heat, basically. And the more we construct infrastructure in our cities, the higher the temperature will rise in cities. So climate action is obviously on the agenda for policymakers in central and regional governments. And then there's the talk about resilience planning. And I'll just give you an example why it's important. So if we switch all of our bus fleets from CNG or diesel to electric, and we build all the infrastructure that is required for that, then if a power line goes down and it takes up to 2 or 3 days to restore power, then what would happen with people not being able to go to work or move around? And have in mind that mobility is really a basic human right, and we've felt the impact of what happens when this human right is taken away from us and we're forced to stay in one place. Prisons, in fact, are one of the most severe ways that we've invented to punish people, by restricting them and confining them not to move around in spaces. So this is also something else to take into consideration. So against this backdrop, we're seeing some aspects of future mobility dashing straight ahead. For example, there's a lot of private equity investment money being poured into various types of shared mobility business models. So electric car sharing, electric scooters, whatnot, you name it, charging stations, charging infrastructure. I attended a presentation 2 weeks ago at our Institute for Artificial Intelligence in Bulgaria, and the presenter was the chief scientist at Waymo. Waymo is the Google autonomous vehicle company. And the things that they showed us were absolutely amazing. So I'm absolutely convinced that in a couple of years' time, and it's not just Waymo, it's ETH in Zurich, who are also advancing a lot in autonomous driving technology. Hydrogen tech is a big thing now in terms of logistics. There's a Bulgarian company called Dronamics. I'm very proud of this company because I know the founder personally. They are setting up a project now with NHS here in Scotland to deliver medical supplies to remote areas with autonomous drones. And they're already flying cargo between Italy and Malta and doing something similar in Australia at the moment. So certain aspects of future mobility are developing very rapidly, but public transport is lagging behind, and it's lagging behind seriously. And I want to talk a little bit about why. So public transport is still operated in many ways as an industrial enterprise. It's been planned and operated. And there are just so many people involved in the whole process, from policy making to budgeting to setting up operations to procuring to monitoring and controlling SLAs, the ticketing part of it at the end, and the fare collection part at the end. It's when we think about public transport, in my mind, it's not possible to just transform the system overnight, right? We have to be talking about transitioning. So you can do transformation and disruption where you have vacuum, where you have space to pour in money and create something new. But when you have so many people to educate, so many partnerships to build, so many platforms to set up. This is what Mark MacDonald actually had in mind when they mentioned the four-pillar approach. They said cities need power, they need political mandate, obviously from central government, but they also need to work with people to provide them with new skills, to motivate them to exert energy in learning and adapting, which is a very strenuous process, and not everybody can go through this process simply because they don't have the vital energy to continuously push forward. There's the problem of funding also in public transport. And then there's this whole argument where business said, look, all the mistakes that were made in planning cities and investing in infrastructure, we're not to be blamed for, and we should not be involved in this messy situation. So whoever created the problem, they should fix the problem. And that's a paradox, obviously. So you will not find any VC funds, even the newly rebranded wing of venture capitalism, which is called impact venture capitalism, investing in public sector projects, regardless of the potential impact that these projects can build. And I've spoken to venture capitalists and I've asked them, look, cities are the places where you can actually create the biggest zero emission impact, and you can improve people's lives. And I told you why VC dry powder will never get channeled in this direction. I call these problems here, these set of problems and opportunities, the horizontal problems of public transportation. And these are the day-to-day problems. And this is the reason why many city managers are unable to lift their head above the water and figure out a way and a strategy to climb up vertically and catch up with the rest of the mobility and future mobility bandwagon. And it's the day-to-day problem is how do you balance the economic and environmental cost of running public transport against passenger comfort. And passenger comfort is a variable that has several components. It has the crowdedness of the vehicles and the comfort of the vehicles. It has the journey connection times and the overall A to B connection time. It has the modality interconnection and the modality split aspect of how do I finish my last mile? Can I take a scooter? Can I integrate it with my travel pass? How free am I to choose how I pay for the service and how I get around? What are my alternatives to do so? So unless cities are able to find solutions to these horizontal problems, it will take a long time for them to start thinking about the vertical ascent and catching up with the other disruptive trends in mobility. So that's the end of the context part. How much time? Very little time. And now I'm going to move to the technology and the solution part. So as I told you, the good news is technology's arrived and it's fairly accessible, and you definitely don't need to have the same resources available to you to build data pipelines and machine learning operations environments. So this is an example of how we've set up some of our data-driven systems. Everything here is open source. So from the abstraction layers to the microservice communication layer, the observability, deployment, application storage layers, business layers, and so on and so forth. And Apache Kafka is a key component that we use in our systems. That's why we call them event-driven systems, and I'll show you why in a bit. But this is what an infrastructure chassis would look like. I don't know if this is too technical for you as an audience or not, but in several of our projects, we've had to use bare metal, and we've had to co-locate it in data centers connected with dark fiber between them. And that's the old school part. Everything from there on is software-defined storage. We have experience with Ceph, virtualization, containerization with Kubernetes and Rancher, deployment pipelines built with Jenkins, not only Jenkins. And obviously, if you're working with big data, you need to be able to deploy the periphery system or the edge system, as it's known. This is the IoT component of any big data system. That's where we sense and we gather the data, and we also engage customers by providing services to them. So whether they are digital payment services or something else. So there's always a physical layer on the edge side. It could be QR codes, ticket vending machines, NFC readers for contactless taps or closed loop taps. CCTV, we use a lot of image, what do you call it? Image modeling, and I'll show you what I mean in a little while. Then the communication layer, gRPC, MQTT, OpenVPN, and again, the deployment layer, the business presentation layer, and the monitoring layer. So all of these tools have saved us millions in operations cost and in personnel cost, because if you're actually able to put the whole stack together, then you can rely on a relatively small team to observe, monitor, and maintain, both on the back-end side and on the edge side. So once you've set up the data gathering process and you've actually managed to transfer the data to the back end, you've managed to structure it, clean it, and build the data pipelines, you can, with today's technology, build your own machine learning operations environment. And we've used Kubeflow for serving models in production and load balancing, and that's this part here. So what happens here, for example, is we collect, and I'll show you the use case afterwards, but we collect a huge amount of snapshots from CCTV cameras in all the buses, trams, and trolleys in the city where I'm from. And we've trained our own model to count the number of people that are on the vehicle at any point in time across the entire network without using specialized equipment. So these are off-the-shelf cameras. So what happens here is a Kafka topic would ingest the snapshot. There's a storage component here, which is not important. And then the machine learning operations part of the data science work that we do starts over here. So this is an instance of the model that we have trained And we use a machine with 8 GPUs. So obviously you would have 8 instances, and Kubeflow would also serve as a load balancer to balance the traffic between these 8 instances. But when the model returns the count is then further processed. The flow is split in 2 directions here. This is where we send the data for historical storage, and this is where we expose the data to a dashboard. And the dashboard would look something like this. This is part of Sofia, vehicles online, buses, trams, trolleys, electric buses, the active vehicle count, and the passenger count at any given point in time. And being able to understand how many people use your service at any point in time is a critical element of solving that horizontal equation that I talked about earlier on. Now, I'll tell you why in a bit. But you know, if you run the data, just the statistics without the predictive forecasting for 1 month time, you will see this is a situation in Sofia, and this is post-COVID actually. And white and green shows you that basically your fleet is underutilized. And the orange and red part show you that between 50 and 100% of your fleet is being utilized. So that's a lot of money spent on service, which nobody uses at the moment. So if you want to prototype various types of solutions, change line topology, stations, adjust schedules, you can afford to go wrong, and you can very quickly find out where you went wrong and correct your assumptions. And that's a big part of what we do, failing fast, rapid prototyping, and then scaling the technology that seems to work. This is another example. We are analyzing an A to B route of a line. In this case, it's bus number 11. And what we can see here from historical data is that we can optimize the duration of this line from 53 minutes to 42 minutes. And that's over 20% optimization. So if you are able to optimize an A to B journey with more than one hop, so one change in line from an average of 75 minutes to, let's say, an average of 55 minutes, then that's a very valuable offering for people who don't typically use public transport. And they will take that into consideration when choosing how to ride, whether to go on their car or use another mode of transport. And how do we know that we can achieve this optimization? Well, basically, we can see that the average speed of the bus based on historical traffic data can be improved significantly in some places. So when you have this kind of information, this kind of a mechanism, so the pipelines, the machine learning, the capacity to build the right models, you can come up with efficiency indexes. And in this case, we have a line efficiency index, and we're comparing the line efficiency of 2 bus lines for the 16th of September. Obviously, one line is performing much better than the other line. So you can also do that. And what we take into account when we build efficiency indexes are things like waiting time, lack of hasting, lack of delay, optimal crowding, and so on. Just a moment. So if we are able to build pipelines with all this kind of data here, and I'll tell you a little bit about what we do with data that we buy, essentially anonymized data from mobile operators. And if we have the methodology to do the data science part, and obviously the technology to do the data science part, we can avoid situations like this. This is an origin. This is a heat map that we built from telco data, and it shows you origin destination patterns, and the red dots are actually the stops of a line. So you can see the discrepancy between the line topology and the actual mobility flow in the city, and we can avoid these type of things. So essentially what I'm getting at is that we can solve the horizontal problems, and we can enable cities to think about network hybridization. And what's network hybridization? It means that if you want to introduce an on-demand transport service, and you want to integrate it in a smart way with scheduled transport, then there are ways to both evaluate the efficiency of a scheduled transit line and also identify, these are called centroid polygons, and you can identify points of interest and areas of potential stops where you can intersect one service with the other service. So obviously this is of huge value for the on-demand transport operators, because with this information they can parameterize the algorithms in their service. So I'm rushing, 5 minutes, rushing. So think about this information that we are now able to figure out what to do with it and to store it locally as a new type of programming language. So we are in fact developing the functions, we're developing the libraries, we are developing the framework to program semi-autonomous public transportation. We know if we have to take down drivers from vehicles in portions of the fleet, we know how to program these vehicles to interact with the rest of the network. Very quickly, the use cases. This is what we did in Sofia. Every vehicle in Sofia has between 3 and 6 cameras. We download 2 terabytes of data every day. We developed our own model based on 50,000 snapshots. Obviously, we had to take into account some specific situations like not double counting reflections in glasses, not double counting people who are waiting to get on the vehicle but are outside the vehicle. Taking into account when 2 cameras are looking at the same person object, all of the things like that. So this is just one of the things that we were able to do. And something else we were able to do is many cities collect streams of transit data. And we do the same in Sofia. We combine public transit data with alternative transit data. And here we've collected information from a scooter operator, an electric car sharing company, and the charging stations. But what we did on top of this is we connected this data to the machine learning environment. So we exposed the APIs at the machine learning level, enabling companies to test their models and algorithms instead of trying to figure out how to use AWS to set up machine learning and developing this competence in addition to proving their business model. And finally, thing that we are most proud of probably is these are a set of schedules, and this is the Pareto outcome of the genetic algorithms that we run in order to find optimal schedules. And this is a very extreme optimization example. So this is the old schedule, this is the new schedule. And you can see that we've reduced threefold the number of courses. These are the number of courses, obviously the number of vehicles, the number of driver shifts. And I chose this example just to prove a point. This is what the occupancy in the vehicles looked like before we optimized the schedule. So the white dots are, and the pale dots are, means that there are very few people on board the vehicles. And the slightly pinkish and red dots means that we've managed to reach a crowding level close to a coefficient of 1. And I'll explain what a coefficient of 1 is. And I'll do it now. Coefficient of 1 means that for every seat in this particular vehicle model, and we know for each model how many seats are available, there is 1 person counted in the seat, regardless of whether that person is standing or sitting. So the new schedule, what it does, and how counting passenger helps here is we increase waiting time at intervals when we know there will be very few people at the stations. So the potential social discomfort and negative impact of implementing a new schedule is very small. You can see at rush hour times, there is hardly any change in how the schedule performs. And you can see on the other hand what the average crowding level would look like then as well. We've increased the average crowding level, but it still remains between coefficient of 1 and coefficient of 1.2, which hardly will cause any discomfort and will optimize the fleet to a much bigger extent. So this is what I wanted to show you today. And if I want to give you the floor. Thank you very much. I gave you the floor and they just took it away from me. Sorry.
Well, so it's a double-sided question. You can answer whichever you want. First one is, how do you manage to, is it part of the algorithms and everything to combine the information from the different sources that you use? As you said, the cards, the QR codes, and the actual count from the cameras, so that you get to a reliable data rather than having duplicates, etc. And the second one is, to what extent you're able to not digitalize, but automate everything, and where does the human factor come in and needs to be able to start taking decisions?
I'll start with the second question. The human factor is the critical part of the equation. When we propose the new schedules to our city, the public transit operators weren't very happy that they would have to reorganize their whole operations, even procuring services such as how often the buses need to be cleaned in relation to how many buses will be used. Driver overtime and syndicates got involved as well, and they weren't happy about all of these optimizations as well. So these are all behavioral models, and that's why I started with the context introduction, because you cannot run through these and pretend they don't exist and just overpower these type of problems. You have to understand them and find ways to work around them. So there are a lot of challenges ahead. And then your first question about the data. So we discriminate between the different data streams and different types of data. And we use different models for modeling. For example, we used DBScan to analyze the telco data sets, but in other situations we would use other methods. So I'm not a data scientist. I really can't go much further into the science than this, but if you're interested more, I'll just connect you with some of our guys.